This video takes a bird's eye view to explain the concept of learning unknown parameters by the method of maximum likelihood. We talk about what is the log likelihood function of a model, how to find the maximum likelihood estimate, and why at all is MLE such a big thing. I finished the video with a quick summary of long and small sample properties of the MLE estimates and a quick excursion into bootstrapping standard errors in small samples. So let's start. Assume you observe a time series of returns. Now, further assume you want to explain that return time series with a specific parametric model that depends on a parameter vector theta, and that implies a joint probability density function, which we call f. So we would write that joint density function as here. Now, any joint probability density function is simply the product of conditional densities and one marginal density, as highlighted here. Let's look at two examples that you often come across in finance research. First, if all returns are independent of each other, the joint likelihood simplifies to the following expression. Second, if returns follow a Markov structure, it means that today's return depends on yesterday's return, then the joint likelihood coincides with the following expression. Estimating a model with the method of maximum likelihood means you want to find the parameter vector theta that maximizes the joint probability function. In order to highlight that this joint likelihood function depends on theta, we often write that as follows, or we simply use shorthand notation L of theta. The value of theta that maximizes L of theta does also maximize the log of L theta, because the log function is a strictly positive monotone transform. Numerically, optimizing the log likelihood results in a more stable routine. I'm going to provide you now with a big picture overview of how to find the theta that maximizes the log likelihood function. There are three classical optimization approaches to find the MLE, which we call theta hat ML. There's the analytic optimization, the grid search, and the numerical optimization. Now let's add a word to each of these approaches. Let's start with the analytical optimization. If the log of the likelihood is given as an analytical expression, one can calculate the gradient, meaning you take the first order condition with regard to the parameter vector theta. You set that to 0 and you solve the resulting equation. If the second derivative evaluated at that theta hat estimate is negative, you know that theta hat maximizes the log likelihood. Now let's say something about a grid search. The grid search works well, but might not always be applicable due to its inefficiency. If you know that the parameter theta lies in a subset, you can do an uninformed search within that set. Basically, you evaluate the log of the likelihood for all theta in your subset, and you pick the one that produces the largest log likelihood value. That approach is applicable if theta is one-dimensional and if the subset is really small. Now let's turn to the numerical optimization. That is basically the smart way of performing a search. There are local and global optimization routines. The local optimization routine starts from a starting value for theta and goes uphill until it finds a plateau. Now you wonder how to go uphill. Well, based on the start value, you determine the first derivative of the log likelihood with regard to that specific value of theta. If the derivative is positive, it means increasing the value of theta a little bit is going to increase the log likelihood. The plateau that the local optimizer finds is usually only a local maximum. And that now is very important, because you want to find the global maximum. So either you have to run the local optimization with very many different starting values, or you use a global optimization routine. There are different global optimizers out there. Most, if not all of them, contain a stochastic component that allows to jump by chance from one plateau to another. I now focus on the last item of this video. Now, the question is, what are the statistical properties of the maximum likelihood estimates? Well, we distinguish whether the sample is small or large and start with the large sample properties. In large samples, the MLE estimator for theta has the following 4 characteristics. First, it is consistent, meaning that the plim of theta hat ML equals theta. Now that says that as the sample converges to an infinite length, the ML estimate for theta gives you the correct population parameter. That's really good news. Now second, the MLE is asymptotically normally distributed. That means that theta hat ML follows a normal distribution centered around the true population parameter theta and having the variance that coincides with the inverse of the Fisher information matrix. Third, the variance of the MLE fulfills the Rao-Cramer lower bound, which says that the MLE is the most efficient, unbiased estimator. And remember, most efficient means it comes along with the smallest variance, meaning with the highest precision. And fourth, there's an invariance result. It says that if theta ML, which is the maximum likelihood estimator of theta, if you found that, then G of theta ML is the maximum likelihood estimator for gamma, which just coincides with theta evaluated through a function G. Now that means that rather than estimating a parameter theta, we could also instead estimate some function of it, G of theta, and then recover the MLE of theta from inverting G of theta. Now let's turn to the small sample properties of MLE. Well, it might come as a surprise, but the small sample properties of the ML estimator are not that well understood. It means that the estimate might be biased, the standard errors might not be well identified based on the inverse of the information matrix. Well, that doesn't sound only shocking, it is shocking in a sense. So therefore you should take away that you need at least 100 data points as a rule of thumb to make informed decisions using maximum likelihood estimation. And now let me complete with a final note. If you apply maximum likelihood on a sample of less than 100 observations, you could try to get the standard errors by bootstrapping. The idea would be as follows. Assume we want to obtain a bootstrap estimate of the standard error of our theta estimate. Now suppose we have 500 random samples from the population. From that, we could get 500 different estimates of theta hat and calculate the standard error of theta hat as the standard deviation of these 500 estimates.
Got feedback? We would love to hear it. Please drop us a line. And if you liked the video, give it a thumbs up. And don't forget to subscribe to the channel.